Alright, can you do it this way? Perfect. Alright, so hi everybody, I'm Alex. Today we're going to be talking about scaling up test on compute with latent reasoning, essentially recurrent depth LLMs. So just table of contents, I'm going to give some background with a mini game first, then we're going to cover model architecture. We're actually going to cover performance first because there's a lot of things to go over in performance. And after that, honestly, the most fun part of the model, but we need to cover everything first, which is the latent space analysis, which is interpretability. Like what's actually going on, like in human terms. So yeah, let's go into, I'm not going to spoil that. Let's play a mini game, and you're going to act like the model, and I'm going to act like the user. You don't need to say it out loud, just like think about the answer. But like, here's a very simple prompt. What's 1 plus 1? Follow along, the answer is 2. Now, second prompt, again, very easy. The answer is 4, right? Third one, you guys should all get this. This is all really easy. Like, the answer is, anyone? Come on, you only have to predict one token.
5.
No, it's not 161,000.
Yeah, I got one of the digits.
You did get one of the digits. So, yes.
Quick question, the tokenizer, is this all represented as a single token?
I'm just playing, like this is just for the game like aspect.
No, I was just curious to see like if this whole thing was a token, that would be really bad.
No, okay. No, I'm just like trying to exemplify the game of if you have to answer in this format, you can't, it's very hard, like for you to actually answer for that last question, you need to have like some additional thought. And regular LLMs, like the current way, does anyone not know what chain of thought is? Okay, so you two, you three. So chain of thought is when you ask, like the very TLDR is when you ask an LLM like ChatGPT, show your steps or go step by step. Which is essentially you want like the model to show its explicit thoughts, and that will allow it to explain how it's getting things. So for example, for the last question, it might be like, oh, 3,589 times 5,678 is this number. Then it will do the second part, and then it will do the third part, but it writes it out all explicitly. And so that's basically what's going to happen in most regular approaches, and I'm going to cover a little bit more. Let's quickly cover what computational depth is in regular transformer architecture. Basic idea, and this is more for reasoning, like understanding what reasoning is. If you have a sentence like this, like John's father is Mike, Mike's father is Tom, John's grandfather is who or whom, you want your model to answer Tom, and there's a bunch of relationships, and so you kind of have to reason to understand what's the final answer. And so if you looked at it from a model perspective, the only way that a model can actually get to the answer in one pass-through is it's highly dependent on the number of layers. You have to make a connection that John is Mike's father, then you have to make the connection that Mike is Tom's father, and therefore you have those first two steps, and then you have to make the final connection that because Mike, which is Tom's grandfather, so like, the grandfather is John. That's the very basic idea of like why, like how reasoning at a very low level works in transformers is you're depending on the number of layers to get some sort of complex reasoning. Like that should be very, to some extent, like obvious, which is you can't understand something deeply if you don't even have the computing power to understand it. And that's actually very limiting because if you have a lot of information and you're trying to make very deep connections, it means either your model has to go very slowly and make very simplistic views, or you just need to make a bigger model to actually get enough layers to actually reason properly. And you hope that it will reason properly. And then there's two main types of reasoning. So the one I was talking about, which is verbal reasoning, that's essentially what happens in chain of thought, is you're explicitly saying everything that happens. Think of it as like if you're explaining to a 5-year-old what's happening, and they want every detail. So like, this does X, this does Y, etc. Literally, if your inner monologue was explicitly written out. The problem is in practice, this requires a lot of steps, which is actually really expensive. And it's actually also very naive because that's not how real reasoning happens in humans and like animals. Like for that example, for example, earlier with the numbers, like in the minigame, your reasoning wasn't super explicit in words. Like if you actually try to answer, you have internal reasoning between the neurons in your brain, and it's much more complex than that, and you can have loops of reasoning. It's not just, you don't just verbalize it and hope you get the final answer. In practice, it actually is really good because chain of thought works, and like that's where you get teams like DeepSeek, which make amazing model, and like basically every big LLM right now that works really well uses some sort of thinking system, which is based on verbal reasoning. The goal of this paper is going to be really about the latent reasoning, which is the word latent is just like some sort of hidden representation. I think that's like the TLDR way of explaining it. And so we want to have some sort of space where we're thinking about what's happening, which doesn't necessarily need to be verbal. So for example, if you think about math, you might think of math in a verbal way, but you might also just not, and it's impossible for you to explicitly tell someone what's happening. You just do it. And that's implicit in how humans think. This is also what happens because you don't just say anything that comes out of your mouth, you think about it first, hopefully. And again, so this is more for LLMs, but not all tokens are equal. If I give you like that math problem from before, you don't really care about what is in particular. What you care a lot about is going to be those tokens that give you information, and then this very last token. Those are the really important ones. So really, they're like, not everything is equal. And so why would we want to switch? So like, there's a few reasons. The first one is verbal reasoning is actually crazily expensive to run because you require so many tokens. And LLMs actually cost a lot of money to run with that many tokens. Like ChatGPT, if you run a basic command, can take up to 3 minutes of compute. That is a long time for a big company to have like hundreds of thousands of users. And they're also incredibly expensive to train because if you want to train something with chain of thought embedded in it, it means you have really long sequences in your training data. And so that's very expensive to train. Latent reasoning, on the other hand, you use compute heavy, which is you don't want your model to be a fixed cost of running on every token. Instead, sometimes you want to scale based on how much compute you have available. So you can actually increase the computation, but you don't increase the size. So increasing the size is like increasing VRAM, which at this point is really the biggest roadblock. VRAM costs a lot of money. Like that's how NVIDIA is worth billions of dollars at this point, or trillions. But you also allow yourself to have smaller parameter counts, which matters a lot if you want to do research, for example, because most people cannot train a model above 7 billion parameters. Like this paper, which had access to really big compute power, still struggled to get a 3.5 billion model parameter out. Also, all of this is open source and open code, so you can train the model yourself. Super open model, super cool team. And we're also going to focus on thinking instead of memorization. That's also a major problem is how much of what you're asking in LLM is it doing things on its own versus it just having seen things in the past. Like if you ask a model to code, I don't know, like reversing a binary tree, it's done that 1 million times in its training data. It's probably not reinventing the wheel. If you're asking it anything new, it's probably going to struggle a lot because it's memorizing, not thinking. There are some proofs that verbal model can think, but they struggle a lot more with it. They're much better at memorizing like general things and then just spewing them out and then making you think they're intelligent. Kind of like the Chinese man, like the Chinese room, where like you have a man who doesn't know Chinese, but he just memorized how to do a bunch of things. And so you think he's perfectly fluent in Chinese, but in reality, he doesn't know anything. He just memorized a bunch of rules. He's not actually thinking about it or like doing proper translation. And then we're going to cover like how we can actually make this happen. Very quickly, I do have paper notation. I'll just keep it open on my tablet for now because I personally struggle with following things if I don't remember the notation. And I'll just keep it here mostly for my convenience and also for yours. So if you have any questions about like what does this mean, I can at least refer back to like the original notation quickly. Basically, model architecture is actually pretty simple.
Can we swap it? Can you put paper notation on there? Yes.
Like that?
We're recording only the screen of the lab.
Yeah, that's fair. So model architecture, okay, let me try to make sure at least I'm nicely. Model architecture is basically made of 3 big blocks. You're going to see here. So you're going to have a prelude block and a coda block. Those are very reasonable, normal, like LLM blocks. Those are just like self-attention. Those would be like just a bunch of layers you would have in a regular LLM. What's really important now is the recurrent block, that green block right here, which is effectively going to be reused a bunch. Now, you might recognize this as being basically what every recurrent system in AI is. Like, that's what RNNs are. And honestly, it's true. Like, they explicitly say in the paper, like every decade, someone reinvents the wheel and goes back to recurrent networks, and it started with RNNs. Then it was diffusion, and now it's this. And so here the very basic idea is, so they will use hello as like the token. So you have the token hello, and you feed it into your prelude, which is like the first block of your model. And then that's fed through a recurrent block. So effectively, you're feeding the input hello, like the input for like the output of the prelude into a block. And it's creating those states, intermediate states, S1, Sn, etc. And that's going to get fed into every block forward, all the way until you get to some recursive, like to some end at the end. Like after a certain amount of iterations of going through it, you're just going to take that very last hidden state and you're just going to feed it into a coda block, which is just going to be like, hey, let's translate that into whatever output we actually do want. And so you'll also see that we're injecting back the input from the prelude into the recursive blocks. That's pretty standard actually in ML because you just don't want to lose the original information. You don't want to erase it over time, so we're feeding it every time. And the very first state is just going to be normal distribution. So it's just going to be some Gaussian noise that we decide. There's going to be a variant on it later, but for now, that's all you really need to know. And the current block is the same everywhere. And that's basically the idea. Yes?
I'm not sure if I'm getting ahead of myself, but when they're performing the analysis, right, you have maybe like an optimal amount of times to recurse in order to get the ideal answer. Do they try, like after each recurrence, just passing it directly to the coda block and then seeing what the performance is as you scale the test?
Well, a lot of it is going to be based on the number of recurrences.
Right, okay.
Like that's basically the entire analysis is going to be number of, like, 2 things, but you'll see, like, that's the way that the analysis is done is number of recurrences and what the hidden state actually means. You could, in theory, try to interpret what the hidden state means at every step, but some of it might actually make less sense. You really only care about what the final output is, because that's how the model was trained.
Well, the recurrent, like, is it a conditional recurrence? Do you always recurse the same number of times? Or
I will go through that.
Okay.
And actually, so very quick remark, I mentioned diffusion. Is this diffusion? The answer is no. The very simple answer is they actually did try to input some, I guess I'll move forward now. They try to input some noise into that hidden state at every step to see if it would have the model, and it just didn't. And path independence, I'm going to go more into depth later on, but like the basic idea is, can you also consider like whatever whatever iteration I you're in, because like this is I is equal to 0, this is I is 1. They also tried that, and it also didn't help. It actually stops the model from generalizing. So, yes.
Sorry, just to clarify, is R of I, is that just like a singular weight and bias, or is it something more complicated?
So that's the recurrent block, which is a bunch of layers. And so here what they mean by using the current step is basically the default S, like S of I, is you feed in as input, you feed in E, and you feed in S of I minus 1, and you get the new S of I. So R is just you can think of it as literally a function. You take an input and you take an
I
output.
was having to just clarify to make sure it wasn't just a single weight matrix.
Yeah,
okay.
that's why I'm going over this, because here the I is a little misleading, but what they mean is you just feed in the actual I. And this actually does interfere a little bit with the way the model works, because you're giving it a little too much information explicitly, and that actually fucks up your model. So we're not going to give it that. And now this is the thing you were talking about, which is how do we actually train the model to be good? I can go back to paper notation if you want, but I think model architecture might help more people. Which one do you guys want?
Second,
Model architecture is better? Or okay. So training the model, the basic idea is we're going to use a random number of iteration to train the model to think in different depth. Because again, if you want to train your model to go through a recurrence block and use that to think, you don't want it to act like it doesn't have any changes. You don't want your recurrent block to be constant, because otherwise that doesn't make your model think. It's just a bunch of extra layers. Instead, you want it to be different sizes of layers, and because it's recurrent and it's random, it's not really going to know how many it has, so it has to be using making the best use out of the layers it does have. And that's kind of the basic idea of how you reason. It's kind of like you in person. You can think about something for longer or for shorter, but you still need to have the ability to think. And you don't want to just use one pattern every time. And so here they just use a log normal Poisson distribution. Complicated looking for the loss, but the very basic idea here is going to be you use this log Poisson. Again, very simple. You just look at how many iterations do you want to do. On average, you want about 30, 29 to 30. So most of your iterations, you want to fall within that ballpark. And they use the log Poisson explicitly because sometimes it can go really deep, so you can make a model that thinks a lot. And sometimes you just stop at 0, or very close to 0.
This is not input dependent because you're just sampling from the distribution, right?
Right.
So
this is for training.
Right.
For inference, there's two ways. Sorry.
Okay, no, I'll let you go.
So inference, you're going to have two ways. Either you do a fixed number of iterations after your model's been trained, or you iterate until that hidden state, S of I, stops moving. If S of I is basically the same, your model has converged on its final latent thought, and at which point it doesn't really matter. And that's actually something really cool because in analysis, because you can identify which tokens are the ones you need to think about and which ones are the ones you don't need to think about.
Nice.
Yeah. A lot of this model, this paper, goes all over the place and is connected back and forth. So I'm trying to make it, straightforward as I can. Yes.
How did they arrive at median is 29? Or is it just understanding?
So they wanted it. So the very basic answer is multiples of 2s are nice, and they want the model to do really well around 32. So they train it around 32 because that's based on how much compute power they have. And then they use log Poisson for whatever is the closest to 32. Because 32 is a nice number, you have smaller and you have much bigger. You have 128 and 256, etc. Or you can make smaller with log base. Really nice distribution for them, I guess. And then the last thing is for backprop. Isn't super important, but for the people who want to train this, you only backpropagate through the last few iterations. Here they chose 8 because 8 is nice, and 8 happens a lot. Or if you have less than 8 iterations to go through, obviously don't go through more. Basic idea is you have vanishing gradients, which for people who aren't too well versed in ML, basically means when you backpropagate, when you update your weights, at some point the weight updates become very close to 0. And so you're basically not changing anything, and that happens if you have really big models. but you still get that prelude, like that blue block over there. It still gets updated because of that input injection, where you output whatever the prelude outputs. It's still being fed through every recurrent block. So even if you only look at the last 8 recurrences, this is still getting back propagated. So even if you only look at the last 8, it's always going to get propagated, and you can do it, like, for example, with the average of the backprop with the injections. So, yes.
So with reasoning models that are quote-unquote thinking models, right,
Mm-hmm.
that they often follow different chains of thought. So you have one sort of line of reasoning that is discarded, and they start another one if they basically see that, okay, this is a dead end.
Mm-hmm.
This was very apparent with the deep sea car one, right? Does this model have that same property where before the hidden states converge, it actually like varies a lot, or is it just consistent to some conversion?
That's going to be very important towards the end, so I'm going to hold off on that.
Okay.
But spoilers, there are patterns that they do identify in like the way it handles things. It doesn't explicitly figure out like I've done something wrong.
Okay.
I don't think they've explicitly shown it, but they have shown like there are ways of patterns around the final before or if they do end up converging with that past state. But I'll hold off a little bit on that. Then I'm going to go, because they actually do cover, like this is their training stuff, and they do have they cover their failures, which I think is really important in research, like cover what does and what doesn't work. The main thing is just going to be that for this particular set of models, the normalization they use, which is RMS norm, and the initialized weights actually matter a lot. And so here they had a few bad runs before getting to their first big good run. And the reason why I show this is because a lot of this paper, if you apply it on only a few thousand or like 0.14 trillion tokens, like 140 billion tokens, it's usually going to be pretty good until a certain point. And here we really want to look at scale. So when you actually want to make this be useful for your company. And so you can see like the very first run they actually did, its main problem is it just didn't get very good, like that's the orange run. And their main reasoning for that is it just didn't use any of the recurrences, it just didn't do well, and they think it's because of the initialized values and the learning weights, which converged to some bad local minima. The second one they did is they actually changed the normalization a little bit. And this one is the green one, and you can see it does pretty well. But what they actually found out is that problem, which is the optimizer step. So here they look at how do you do with different levels of recurrence on some accuracy metric. And they found that no matter what the recurrence level was, it was always the same result. Like they're all overlapping. Like all of these are different recurrence levels, and you can see on the green one, they're all overlapping. So that's pretty bad. I'll use the little laser. They're all overlapping, so that's pretty bad. And another problem here is like if you look at what happens in the correlation between every single latent state, a lot of them are 1, which means it's not even changing the latent state for quite a while, which is actually pretty bad. So then they did a third training run, and that's the main one. And then one actually did pretty well. You can see like the more it thinks, the more it has recurrence, the better it does. The more down it goes, and you can also see that in the fact that it does much better. They attribute some of the failures, particularly of run 2, to again local minima and what they call like a latent representation collapse, which is essentially like your latent space and like that latent state just completely meaningless. The model was unable to use it at all, and it collapsed in of itself. So that's just a very brief like overview of that.
Sorry, so many questions. Poor initialization and poor norm. What is poor initialization in this?
Just the initial weights. There's just some randomness in there, like how you initialize your weights.
Yeah. So what initialization did they use that was good and what was bad?
They just attributed it to just random chance. What they made the final change was they made the learning rate much lower for their final run, and that avoided local minimas.
Interesting. And what about poor norm? Is this gradient norm?
That's because I used RMS. So on their very first run, and on their very last run, they used RMS norm. But they tried to switch it for norm 2, for like run 2, and that's where it didn't use recurrence at all. And so they flipped back to the original step, and then they just made it go much lower learning rate. Yes?
What norm did they use in the second step? Because from my understanding, RMS is basically regular normalization, but without calculating the standard deviation.
I think what they said, I think, is just like whatever regular normalization is, like just some regular norm. I don't think they have like more specific than that, but you can check the
I
code.
was just curious.
Yeah, and then let's just quickly look at like how does this actually perform? Like I've talked a lot about theory, but who cares about theory if it doesn't work? And you're going to see a lot of graphs, but the very basic idea here. So this is a benchmark. You can see of like their model. R is again the number of recurrences, just to be very explicit. I guess now I can move the model architecture. I hope, so you can have it on both screens. So the basic idea here is their model was trained on 3.5 billion parameters, which relatively small by today's standard. But again, this is a labs and they don't have that many resources. They're only able to train one. And they also have very few training tokens, 0.8 trillion. Like compared to other state-of-the-art like of this year, last year, most teams have like at least twice or 3 or 4 times as many. And with enough recurrences, they actually do really well. Like they compete with a model that's twice as big that had much more data with their model given enough recurrences. And that's actually incredibly promising if you think about it from a model point of view. It means that you're able to run a 3.5 billion model, which needs half as much memory. So much more people can use it, and it's much more cost efficient, as long as you just give it a little bit more time to actually run. Again, huge, and costs a lot less to train. And the second thing is training data, where actually a lot of companies are like running out of training data. They don't have more to get. The model, that very last model, the reason why it does so much better than everything else is because the team that made it spent a lot of money and time making really good 4 trillion token training data. Like that's the main improvement they did, and that had a massive effect on their model without changing much of the architecture. But here we're able, with just like some random data they compiled, have a model that beats like their competitors, who actually do spend a lot of time and money getting like bigger models, better data. So essentially here, work smarter, not harder. And there are actually some like ideas as well in the benchmarks. This is a further study, like I'm not going to include it, but the very basic idea is they showed that if you, like one of the major reasons why their model isn't doing super well on some of the benchmarks is just because it never encountered the data. And if you give multiple models the same amount of information, like either in context clues or something like that, like they have an open book test, then it actually does just as well, or if not better than other models. And this actually is like a very good way of showing that your model is doing better than everyone else, despite it doing objectively worse on some metrics, just because it didn't learn that thing in the training, but the architecture actually does enable it to learn that. So that's just a small thing. Like if you guys think that this is impressive, just know like if you do compare it on the fair ground, where it just didn't even learn the thing, again, like if I ask you some random biology topics, you're not going to know, but if I give you the textbook in front of you, you're going to be able to tell me. That's effectively the same problem here. So yeah, yes?
So for these open book tests, how complicated is it to actually get the answer? Like, is the answer just there and you just...
No, usually it's some reasoning thing. Like, again, it's a little bit more complicated, or like, sometimes you have like information there, but you need to interpret it or something like that. So.
Okay, but can you give maybe an example of such a task?
I didn't look too deep into it, but like I think a good example would be like, if I give you some information about like how, like what happens in the conclave, and I ask you like, hey, now that you have this information, like, what is the next step that happens after the Pope dies? Like what does it mean if the chimney, has like white smoke, and like and it needs to interpret the information from the conclave? I'm using the relevant example as much as I can, but like, yeah. Also, I need to watch that movie. Anyways, so did that answer your question?
Yes.
Now, let's talk about the more interesting things where you do need reasoning, because everything before that was actually a little bit more common, like general language models. If you look at the math and like code sections, okay, I still have time. So if you look at math and code, it actually obliterates the competition, except for that very last model, which again had incredibly good training data on a lot of it, and it's also much bigger. But against like similar sized models, which are like even this, like basically 7 billion parameters or 12 billion parameters, with enough reasoning, completely destroys them. And it shows that, I mean, if you want to think in math and when you're coding, and that's where it matters the most, and that's where thinking shows that it's prowess. And I mean, you can see their model with 32 iterations, again, with so much less data, is with only like half the size, is doing better than basically all their competition, except like that 7 billion parameter model on like one of the things. But I hope you can see how like this is truly innovative. Like this is innovative, and it actually does better. That's really the main goal here. And then the next question is going to be, how much recurrence do you use, right? How do you actually use more recurrence to be smarter? And so, again, the idea is, I mean, this should be fairly obvious to most people. If you're using a test that requires reasoning, like math or coding, you would expect your model to need more recurrent steps to think for longer. And that's actually what they found in practice. The more recurrence you give your model, the smarter, like the better it does. So here you have like some easy tasks. Here, which one was it? Like Hella Swag is really easy, and so you actually don't get much of a benefit after 8 iterations. But something like Human Eval, which is coding, you still get benefits up to about 32. Same thing for those two, GMSK, and those two, like all 3 of those, like the last 3, those are all coding. And so you can see how it only really converges at a 32, whereas Hella Swag, which is much easier and doesn't need reasoning, converges much faster. So reasonably obvious, but again, like they actually do have proof to show this is reasoning. This is a model that is reasoning, that is thinking. It's not just doing better because it's trying to do better like for no reason. There is an actual like intelligence there. And again, we can do some more direct comparisons, particularly when you look at on the various different tasks. And again, like those last 32 recurrences and 64 recurrences, those tend to be the sweet spots on all of those really big models. Like again, at the very beginning, your model doesn't really know how to be using its recurrence smartly. But what's really interesting is the more you train your model, the smarter it gets and the better it gets at the reasoning. And you can see like this is not over. They only stopped because they didn't have more money and like better compute. You could keep going with more training data and your model would get better just like a human would. Now, I personally think that's really impressive, but yeah. Any question on this or? Okay. Now another fun thing is, does anyone not know what few shots is? I think, yeah, a few. The basic idea of few shots is if you're prompting some, like let's say ChatGPT, and you want it to like do a very specific sequence, let's say, like again, do some math in a very specific way, like do calculus, and you can give it examples on how to do it. And then the last one is just, okay, now you do it. Sorry, did you have a question? No, I saw some movement. So that's basically the idea of few shots. And you should expect intuitively that few shot makes you think more, because when you have examples, you actually learn how those examples work, so you reason over them. And then because you were able to reason on how the example worked, now you can reason on how to use them. Hey guys. And so that's actually what they found here is, well, lots of people. Basically, if you have 0 shot, which means you're not giving any example, your model only needs to think up to about 12 iterations, like 12 recurrences. But if your model has enough examples given to it, now it can use that big brain of it, like that big brain and that recurrence relation, where it can actually think more. It has the ability and the freedom to think more because it was given enough information to think and to reason. And so you actually, again, this is another proof of reasoning happening. Because when given examples, it is able to reason more. Yes?
This is something very similar to this is also demonstrated in standard, like the standard approach to reasoning models, right? Is there any comparison to how the performance scales for a standard reasoning model versus the latent reasoning model?
So with verbal reasoning models, I'm pretty sure this is also true.
Yeah, but like is the latent recurrence giving a bigger improvement with the more shots or not really?
What do you mean by
for example, from 0 to 5 shot is considered at about 10% improvement in performance. Not true, but
actually, I don't think they did a direct comparison.
Okay.
But I also think that's an impossible comparison to do fairly. Because for those chain of thought models, first of all, they need to be really big to actually work. Like that is one of their limitations.
Well, they compared it to like 5.
The other most of the models they compare them to are like regular models. I should be clear.
Okay.
I mean I guess like there are some Sorry,
but even they improve with a few shot learning, right?
Right. So they also improve with few shot learning. Not as much as this does because. Do I have okay, no, that's different. So I don't think I have like the direct comparison. I'm not actually sure they do give like a nice graphical representation. But I mean, given how they did on previous benchmarks, particularly the thinking ones, it allowed it to reason so much better. It stands by itself. Like if you already do better with 0 shot, and now you do even better with few shots, like this is really big. But here, the main thing is not looking at does it do better with with more shots, because obviously it will, right? I mean, you can see it right here. Like this is basically what happens if I give them like a regular model a few shots on the very left. But as you give more and more reasoning, you diverge. Thinking does help, and here thinking will improve how much you do, and you want to use more and more thinking. Does that kind of help? I guess like it is implicitly shown here because like when you don't think, you do much worse.
I would disagree on that because the recurrent block definition is different, right? I presume the recurrent block is not as big as the entire intermediate layer of the standard reasoning approach.
It's pretty close actually.
Okay, actually then I guess slight backtrack, but could we talk about each of the blocks and how those are constructed?
Yeah, I mean this is actually explicitly said, but it's a little boring. But the very basic idea is you're going to have this is going to have one attention layer, this is going to have 4, and this is going to have 1. I think in their final model they ended up doing twice that, so 2, 4, 2. And when you're training, obviously you're going to have 2 plus 4R plus 2 layers at inference time, where R is the number of recurrences. For each token prediction. So I hope that kind of answers your question. Again, this main point again is to reinforce the idea that your model is reasoning and it's thinking intelligently, and it's able to make connections between what happened in the past and reason with them for the future and draw parallels. Very human-like behavior. We love to draw patterns. If I show you how to, that's how we learn to do math. We just see enough examples. For the most part. Now this is actually pretty interesting. So this is a slightly different chain of thought. I guess there's 2 things I need to introduce here. First one is Kullback-Leibler difference threshold. Very wordy thing. Essentially what we're doing, the very big, I can just draw it. If you imagine this is this is the number of recurrences. And KL is just going to be how similar you currently are to the very last state. So that state is that hidden representation. So we're just going to be this is how similar you are. You could you could even call this delta. And you expect this to converge eventually. And when it gets below a certain threshold, you just stop. and you just use that. That allows you to stop wasting resources, recurrence, like to avoid using more recurrence than you have to. Again, very smart if you have limited hardware. It means now your model can adaptively think more or less. Again, very human, very like reasoning savvy. And the second thing they did here is, so here they call that continuous chain of thought. It is very similar to like other chain of thoughts, but the very basic idea is instead of resetting, here. So you see how that state 0, originally, like on the very original model architecture, is just normal noise. Instead of that, we're going to use whatever previous state was there. Whatever that last S of R, like that final S of R that was entered in the prelude, we're just going to cache that, like save it, and use it for the future. That actually is what they call continuous chain of thought, because we literally keep track of our thoughts over time. And this is just like a fun little test they wanted to do, I guess, like see how that would impact things, because that's essentially what chain of thought is. You use what previous work you did, you use that thought, now you reuse it. It's a chain. And so what they found, and so this is essentially what this graph is showing. This graph is like a distribution of when you stop. So when do you reach that, I erased my drawing, but when you reach that threshold of you stop reasoning more. And so here the default is this like slashed graphs. That's what happens if you don't reuse previous information. So if you just use a normal noise at the beginning of every reasoning. And the new one, which is continuous chain of thought, is what happens if you do in fact use previous thoughts and like previous hidden states. And I mean, this is kind of expected, but because it's able to use work that was already done, you can stop a lot earlier. You don't need as much reasoning, because a lot of the reasoning has already been done for you. And this is really important, for example, for mathematics. You can see how there's a skew to the left, because they've already done some of the work of understanding what happened. It's even bigger on something like philosophy or fallacies, because now most of the work of reasoning, you've already done to understand what even is going on. Like in philosophy, what are you even talking about? In fallacies, what is the fallacy about? And so here, because you've already done a lot of the reasoning, you don't need to reprocess everything every time. Very human again. I don't forget everything I've just said a minute ago and I restart reasoning from scratch. I mean, I could, but I'm not. There are some people with diseases like that and they still perform very well as human beings. So it is still a thing in humans, but yeah. And you will see it a lot more in like logical fallacies, philosophy, like hard word-based reasoning tasks where you really need to have processed a lot of information, but then it comes very naturally afterwards. It's hard at the beginning, easier later, then chain of thought makes a lot more sense. Something more like a moral scenario, honestly, there's not as much to be changed. It's always going to be difficult until the very end. And now we're going to go into what may make some of you happier or sadder, which is going to be the latent space analysis. What is actually going on in that latent space? Is this model being very random? Are we just getting lucky? Is this model actually cheating out of it? Like, I've already kind of showed that it works, but what is actually going on? Let's do some interpretability, I guess. And so the first one I'll give is convergence on the sequence. Can you guys all read what's happening? Is this big enough? Mm-hmm. Okay. So this is a pretty good example of, let me go back. This is a pretty good example of, we're using a fixed number of recurrences, but we're going to track the differences, so the convergence, like the differences between the states to identify like convergence to the final point. So how far are you from the final state that you're trying to get to? And obviously the very first state is almost never going to be the same as the final state. You're going to have some thinking in between whatever your prelude gives you. and whatever your recurrent block outputs. And a lot of tokens, like I am looking for help with, all of those pretty simple. You don't need a lot of reasoning. Now here's an interesting one, bomb. That's surprising. That's honestly not super expected. You might need to do some reasoning. What do they mean by bomb? How many people want to make bombs? And you see here it already lasts a little bit longer. And like the next few tokens are also going to be like that because bomb was so important that, maybe that person is trying to mean like a laughter bomb or something, like a glitter bomb. Maybe it's not an explosive bomb. Like there's a lot of ways that bomb could be interpreted. So it will reason a lot about what is around the word bomb, mostly what's after, because bomb is what's important. Again, household is not that important. It's very easy to understand. Household there's very little thinking to do about that. And now it's getting very, very, very interested into the really wronged me. And I mean, it should make sense. If you see something really wronged, that's really the core of the sentence. Yes?
So, I'm a little bit confused. This actually looks extremely similar to the Poisson distribution that we had earlier, where if you look around 30, that's usually when the model ends up converging in latent space. But there are a few cases that go extremely to the other end and a few that are a little bit shorter.
That is true. And again, that's why they train on 32. Like, you will see that here because most of them are trained to fake on 32. Like, that's why you will see most of them, that's a very good observation. You'll see most of them end around here. Yeah.
And then also, is this down to the data requiring more reasoning, or is it just the actual Poisson distribution? Because during training, we are sampling the number of iterations.
This is on a fixed number. This is on 64 recurrences. For this type of I should have explained that, I guess. That's my bad. Here, every single token is being thought about for 64 recurrence blocks. This is just for interpretability, because obviously the alternative is you would just see like this is done after, I don't know, like 32 states, 25, etc. But here, like they wanted to show, if we keep everything the same, can we actually look at what's happening in terms of how are you converging? And it allows you to identify those really important tokens. You might identify them with attention in regular transformers, albeit you're probably much better of an expert than I am at this, but what I don't understand, it's really tough. It's really, really hard to actually find what is the interesting token in your sequence.
I guess my question is, if instead of training with the Poisson centered around 32, you would train it centered around 64, would that affect the latent state conversions or not? Because I mean, the interpretation for us is that okay, the amount of time it needs to converge is data dependent. But is it not just random based on the data that it has seen during training? So, for example, for the word really, if the number of recurrences was generally larger than 30, it just ends up taking a long time to converge versus the average, which is close to 30.
This was trained on a big enough scale, and they've shown this to be on also very like common things like numbers. If you have the number 3, it's definitely seeing most of 3s at around. Again, if you look at the Poisson distribution from earlier on, like there's very few things that go beyond 50. Like the probability of you getting trained beyond 50 is small. So it is actually being it is going to be, again, like a little bit more dependent on the actual token, on how much it thinks it should think on the token, on how much reasoning there is needed, rather than, oh, that's just how much I reasoned in the past, let's reason on it again. And again, 800 billion tokens being trained on, while small to other things, is still enough data to not have that problem. This is trained on scale. I would have fully agree with you if this was trained on only a few thousand words. This is trained on a big enough scale that it would likely have seen those words in different contexts with very different lengths, mostly centered around 32.
does there exist a comparison for something that is a more complicated reasoning task than this, like actual, like the math example that you had earlier? Does it show that the amount of reasoning steps that are required for convergence is significantly larger than this case?
Yeah, they do have some examples. I'll go more into that, but I don't think we'll have that much time. I'll continue on at the end. By Sean. And so, but here what's important to realize is, again, it's able to identify some really important tokens, really wrong, and those are going to be things that it just needs to think more about. There is a slight important remark here, which I think is somewhat important, is the word bomb doesn't converge monotonically. You can see it has like, I don't know how easy it is to see, but like if I zoom in, you can see like there's a wave pattern, right? Like some of them get closer, it gets out, it gets closer, it gets out. And that's how I'll lead to my next topic, which is going to be PCA analysis of the latent space. So most people, I'm assuming, do not know what principal component analysis is. I guess this is principal component analysis. PCA is a way, so our latent states are hidden in some high dimension. Like, I think in their example, it's a few thousand, like 5,000. So if you have a 5,000 sized vector and you want to see how it converges, it's really tough. You can't visualize 5,000 dimensions. PCA allows you to basically only look at the dimensions that are really important. I'm not going to go into much detail, but it allows you to plot the most important, the most important coordinates. So you can think of it as like, let's just look at something that's really big and XY coordinates. That's just going to be the very easy, simplistic way of thinking about it. Take CS373 and like other classes if you want to learn more. And this is like the main important side because I know we're running out of time. I'll go more into depth with people who want to stay after into like the actual paper. So here we're going to see that a lot of tokens, like this is for example a token deeper. It actually like you can see how it's not very straightforward, so it doesn't converge very quickly. So there is thinking happening. Like it's not outright, but there is like some variation. This is on the main two PCA. This is PC1, PC2. So the first most two important coordinates, and this is the second two most. And then this is the last two most, like first six. There's like thousands of PCA. But when we order them, we're able to look at the most important ones. Here, this is the one I was talking about, number 3. And this is the same thing with like something like bomb. But the basic idea with something like number 3 is you're going to orbit a lot. And this is where like the thinking takes an orbital path, because it's thinking in a loop. Like there's a lot of processing and reasoning to be done around numbers. I can go into the actual example where this 3 was taken from, but it was something around numbers. And like the 3 was very important, and you have this circular orbital. Well, like this, it's not very circular, but it is an orbit where it doesn't actually converge. This is actually something that's already been shown in other papers with very different ways of checking it with more regular attention. That for everything arithmetic-based, you will tend to orbit around the final thoughts for quite a while. What this paper has found, which I think is pretty impressive, is because it orbits not only on numbers, but on other tasks which require a big level of like reasoning. For example, again, like if you're trying to follow step, like who is my grandfather, and I give you like a bunch of fallacies, it's going to take a similar reasoning approach as you would with numbers. It's actually thinking, rather than just like pattern matching. It won't fall into the fallacy because it's thinking through them. And then the last one is going to be something like wrong. Here you can see on the first one, it tends to be pretty good at finding the final one, like it jumped around. But on some of the PCAs, it actually has that straight line. And this straight line, they don't have a conclusive proof for it, but what they think the model is doing is it's using it to count the number of iterations. We didn't tell the model what the number of iterations was because we wanted some path independence between, we didn't want it to act like a regular model. We wanted to adapt to the number of learning steps it could have, or like the number of recurrent steps it could have. Here the model intuitively was like, well, sometimes it's useful to actually know which step you're on. Because if you're going really far away, it can be useful. So that's what their thought is for like that specific pattern. And circular is generally for like difficult to reason on tasks. And I'll try to finish up quickly because I know we all have places to be. So most tokens, again, convert to a single value. Hard questions, you tend to orbit around the final answer. You don't easily get there. Saddle patterns, that's how you count the number of iterations. And this is like the key final thing that I want you to remember. The presence of patterns in the data means that your model is learning to reason on its own. We did not teach it how to reason this. We did not give it data and explicitly teach it, do this reasoning. That's what everybody's doing with things like DeepSeek. DeepSeek, you're basically like, well, in some cases, like the way they do it is they make like a model and they use that and then they check whether or not the output is correct and they make a big data set to teach the model how to think afterwards and like what good thinking is. This is fully on its own. It's fully independent. And also it's very difficult for us to know how it's thinking beyond the fact that, oh, there's funny patterns. And it seems to be related to that type of thinking in humans. And I think that's really interesting, like really big in the field of AI because, like, I don't like to say to throw the runner out, but it is getting closer to AGI in the sense of you have a model that's thinking without us teaching it how to think. Whereas other things like DeepSeek, again, you have like that huge step, or like OpenAI, they need to work a lot on their data and like it's a lot more reliant on the company and the people making the model. Here it's reliant on the architecture being amazing. And that's basically it. Like I'll go through some more interesting results with the people who want to stay. But yeah, like my final line for today, which is cheesy, is think about it. Yeah. Thank you. Any questions before going? I'll take that. Oh.
My thought is, I also want to ask you, why do you hate PCA? Or you didn't? Oh, okay, never mind. For analysis, I thought you said that PCA does not work for.
I'll stop the recording.